Okay, Math 282 students. So in this recording, I'm going to be doing an example from section 7.5. 7.5 dealt with the Dirac delta function. And what we have here is we have a differential equation, second order differential equation, and the external function on the right is equal to 1 plus the Dirac delta function at t minus 2. So that means at t equals 2, there's going to be a spike in the system, and that will change how the solution, that will change the solution. The solution to this differential equation has to be a piecewise function that changes at t equals 2. Okay, we have initial conditions y of 0 equals 0 and y prime of 0 equals 1. And what do? Well, first what we do is in our solution, we take the Laplace transforms of both sides of the differential equation. Now on the left, the Laplace transform of y double prime minus 2y prime is simply equal to the difference of those Laplace transforms, okay, with the 2 factored out on the second one. And then on the right-hand side, the Laplace transform of 1 plus that Dirac delta function would be equal to the Laplace transform of 1 plus the Laplace transform of the Dirac delta function. Okay, so the Laplace transform of the second derivative of y is equal to s squared times big Y of s minus s times y of 0 minus y prime of 0. The Laplace transform of 2 times the Laplace transform of y prime would be equal to 2 times, well, the Laplace transform of the derivative is just s times big Y of s minus y of 0. Okay, and then on the right-hand side, we take the Laplace transform of 1, that equals 1 over s. And then the Laplace transform of the Dirac delta function, okay, that is going to equal e to the negative 2 to the s power. And there's a formula in section 7.5, formula 3 from theorem 7.5.1 that gives the formula for the Laplace transform of the Dirac delta function. All right, so now what we want to do is, you know, we're right here now. We're right here. And, well, on the left-hand side, I'm going to put in my initial conditions. Y of 0 is equal to 0, and y prime of 0 is equal to 1. And so I rearrange the left-hand side. Okay, after a couple of steps, the left-hand side is going to be equal to s squared minus 2s, that quantity, times the Laplace transform, which is we denote, as you know, by big function y of s. Okay, that will equal 1 plus 1 over s plus e to the negative 2s. Next thing I want to do then is divide by s squared minus s, and that gets me then down to here, this equation at the bottom. And you'll notice that s squared times s squared minus 2s, that can be written as s cubed minus 2s squared in the denominator. Okay, so really, you know, we just have to be very organized when we do these problems. But now, you know, we recognize that we're going to be taking the inverse Laplace transform of both sides of this equation, and that means that I have to get for each of these rational functions, I have to get a partial fraction expansion. Okay, well, there's really these two rational functions are the same. So really, then we only need to get two partial fraction expansions. So what I'll do is we recognize that here s squared minus 2s is the same in the denominator as s times s minus 2. Okay. And then for this, and that's the same also for this term. And then the second term, s cubed minus 2s squared, in the denominator there, that would be factored as s squared times s minus 2. So now, given this, we can do the partial fraction expansions. So let's focus on the 1 over s times s minus 2. We express that as a over s plus b over s minus 2. And you've done partial fraction expansions many times. You'll find that a equals negative a half and b equals a half. Okay, and so 1 over the denominator s times s minus 2 is equal to negative a half s plus 1/2 s over 2, which is, it's convenient to write it this way, just negative 1/2 times 1 over s plus 1/2 times 1 over s minus 2. Okay, it's just convenient to write it that way. And, you know, I'm going to move forward here, but just feel free to pause the recording if you're, you know, taking this down as notes. You can just pause the recording anytime and take notes. I think that's probably a good idea. Okay, now let's do the other partial fraction expansion. So the other partial fraction expansion, in the denominator, we have s squared times s minus 2. So that's going to then expand out as a over s plus b over s squared plus c over s minus 2. Okay, that's how you do that one. When you do the partial fraction expansion, you'll see that b equals negative a half, a equals negative a fourth, and c equals 1/4. And so the rational function is going to equal then negative 1/4 times 1 over s minus a half times 1 over s squared plus 1/4 times 1 over s minus 2. Let me say it again. So the rational function here will expand out as negative 1/4 times 1 over s minus a half times 1 over s squared plus a fourth times 1 over s minus 2. Okay. All right. So now we can, if we go back here to our Laplace transform expression, okay, this one right here, I'm going to replace these rational functions with my partial fraction expansions that I just found. And so when I do that, y of s will equal everything on the right-hand side. Okay, and all I did was I replaced the rational functions with my partial fraction expansions. And I recognize that we have some terms in common here. We have negative a half times 1 over s. We have negative 1/4 times 1 over s. That's going to equal negative 3/4 times 1 over s. And let's see here. I have also, I have 1/2 times 1 over s minus 2 plus 1/4 times 1 over s minus 2. That'll equal 3/4 times 1 over s minus 2. And then, of course, we have the 1/2, negative 1/2 s squared there. That goes here. And then the term on here on the second line, I just expand that out, as you see here, by distributing e to the negative 2s into both terms. Okay, and so you see before you, and you know that the Laplace transform of y then, okay, the Laplace transform of y here equals all of this, well, it equals the sum of these 5 terms on the right. And, you know, you always want to have things expanded out on the right-hand side. So before then you take your inverse Laplace transform. So of course, to get the solution y, I have to take the inverse Laplace transform of both sides of this equation. And if I do that, that's going to get me then, it's going to tell me my solution y, or y of t, equals the inverse Laplace transform of this entire function of s on the right. Now, the inverse Laplace transform of the sum of 5 functions of s is the sum of 5 inverse Laplace transforms. And naturally, we can factor out the constants on each of those, for each of those. So when I take the inverse Laplace transform, then you know, run it through the 5 functions of s, this is what I'm going to get right here. And now we're at a stage where we're ready to take those inverse Laplace transforms. And of course, for the bottom 2 inverse Laplace transforms, we're going to be using the second translation theorem, as you can see that we've done here. We're going to be utilizing that. Okay, so the other 3 inverse Laplace transforms are easy enough to get. And so then the final answer for y, the final answer for the solution y, is given here. And in WebAssign, they try to be helpful by sort of writing down the form of the solution for you. And then, you know, that hopefully can give you some clues if you don't get a right answer. You know, it gives you a little guidance, okay, to just start off with. And hopefully helps you catch maybe mistakes, things like that. But this is the answer. This is the answer right here. So now, remember, this unit step function here is equal to 0 when t is between 0 and 2, and it equals 1 when t is greater than or equal to 2. And so our solution function, our solution function y of t will then equal this piecewise function. And again, at t equals 2, you had that spike occur, that jolt occur, the Dirac delta function, and that then introduces this extra function. Okay, and so I hope this was a nice, helpful example, and I think actually it's even helpful for problems in section 7.3, particularly the partial fraction expansion part. I think it can be helpful as well for those problems. You know, the later ones where you had to use Laplace transforms to solve differential equations. Okay, so I hope this was helpful, and thank you for listening. Okay.